Hello everyone. So far for all the integrals we've done, we had to recognize the antiderivative of the thing we're integrating. So we used antiderivatives, but quite often we don't recognize the antiderivative of the thing we're integrating straight away. Maybe it's a complicated one that's not a standard antiderivative. So in that case, it's nice to have some other techniques. So in this video, we're going to walk through one such technique, which is called integration by substitution. And first we'll talk about it for indefinite integrals, and then in the next video, we'll talk about it for definite integrals. And it's going to be roughly the same in each case, just with one small change. So let's see how it works. So suppose u equals g of x is a differentiable function whose range is an interval I, and f is continuous on I. So this is just saying that the functions are nice enough, and f of g of x makes sense, so we can compose them. Then the integral of f of g of x times g prime of x is equal to the integral of f of u du. Okay, so what is going on here? This is saying that if we have something that we recognize as, so we're integrating something that we recognize as a composition function times the derivative of the inside, then one way to actually do this integral is to use a substitution where u is the inside function, and then instead integrate f of u with respect to u, all in terms of u, get an answer in terms of u, and then at the end, after the integration, replace u by what it was in terms of x. So here is the kind of theory, the result in abstract. So how do we actually implement this? So we have to recognize what we're integrating. So we said it should look like a composition times the derivative of the inside. And then we should consider a substitution u is the inside function. And then once we've done that, we need to rewrite everything in terms of u and du. So rather than having x and dx stuff, we need to have u and du stuff. So how do we do that? Well, we can do the substitution straight away. U is g of x, right? U is the inside function. That's why we chose u. And then we have to get rid of the dx part. So to move the dx part to a du, we have to use the equation du of dx equals g prime of x, right? If u equals g of x, we differentiate both sides, we get du dx equals g prime of x. And then we can basically manipulate this fraction however we like, so that in the thing we're integrating, we manage to change the dx into u or du. So for instance, here we could write it, if we recognize the g prime of x, we could write it as du dx and then cancel the dx's. Or we could multiply through, we could write du equals g prime of x dx and dx equals du divided by g prime of x. We'll see in examples how it works. But the important thing is to take the thing we're integrating and write everything in terms of u and du. And then do this much simpler integral with respect to u. And then at the end, once we've integrated, we get an answer in terms of u, then we replace u by what it was in terms of x. So whatever was that substitution. Okay, so it sounds complicated, but the main idea is simple. Let's see how it plays out. So here's an example. Find the integral of 2x times the square root of 1 plus x squared dx. And okay, there is a complicated piece and a simple piece. So the complicated piece is the square root of 1 plus x squared. And this is a composition function where the outside is the square root of u and the inside is 1 plus x squared. And we also see the derivative of the inside appearing, right? The derivative of 1 plus x squared is 2x. So this looks like composite function times the derivative of the inside. So we said that this is a prime candidate for doing a substitution where u is the inside function. So let's try to pick u equals 1 plus x squared. And then we want to somehow write the 2x squared 1 plus x squared dx all in terms of u and du. Okay, so if we differentiate, we get du dx equals 2x, so du is equal to 2x times dx. Okay, so if we recognize what we have the square root of 1 plus x squared, which is going to become the square root of u. And then we have 2x dx, which is going to become du. So using these equations, we can manage to write everything in terms of u and du. Okay, so we start with what we integrated. The 2x dx becomes du. The square root of 1 plus x squared becomes square root of u. And now we have a much simpler integral that we can just integrate with respect to u, right? This is u to the power of 1/2. We integrate, we get 2/3 u to the 3/2 plus c. And then on the last step, we are going to replace u by whatever it was in terms of x. So u is 1 plus x squared. We get 2/3 1 plus x squared to the power 3/2 plus c. Okay. And it was really important that when we do this integration, we have to have everything in terms of u and du. So we're not allowed to have anything in terms of x left over. So if you still have things in terms of x, you want to go back and revisit and see how to write that in terms of u, or maybe try a different substitution or something. It's important that we only have things in terms of u and then du. Okay. Maybe another way to write this, so there are various different ways you can do the algebra. The important thing is that you end up with something that looks like u times du. So if here we started with 2x times the square root of 1 plus x squared, we could write, du equals 2x dx, so dx is du divided by 2x. So we would have the thing we started with. We keep the 2x, don't worry about it. We can change the easy one, right? We have square root of 1 plus x squared becomes square root of u. And then straight away we can change the dx to du divided by 2x. And then we get to cancel the 2x's that way. So it's up to you. You can either think about having 2x dx and replacing that by du, Or you can think of replacing the dx by du divided by 2x, and then canceling the 2x afterwards. So they're just two ways of looking at the same problem. And you will get the same answer, of course, once you go to the integral of square root u. Okay, so here we had a very nice case, right? We had a composition function and we had the derivative of the inside. So everything also works smoothly if instead of the derivative of the inside, we have a constant multiple of the derivative of the inside, because then we can just pull the constants out. So for instance, suppose we're integrating the integral of x cubed times e to the x to the 4 plus 1. Okay, well, we have a composition function, so we should consider a substitution. The inside is x to the 4 plus 1. The derivative of the inside is 4x cubed, which isn't quite what we have over here. But as we'll see in a second, if we play around with just the constants are going to be okay because we can pull them out of the integral. So let's try to do our substitution. We have u equals x to the 4 plus 1, du dx equals 4x cubed. So we want to write x, we want to write dx in terms of du. So if we rearrange this, kind of treat it as a fraction. I mean, it's not really a fraction, but for the purpose of integration by substitution, it's always okay to do this. We get dx equals du divided by 4x cubed. Okay, so in that case, let's try to transform everything. So x cubed, we can't do anything right now. Then we're going to have e to the u, and then we're going to replace the dx. Okay, so we get the integral of x cubed e to the u, and then we have dx becomes du divided by 4x cubed. And then we get to cancel the x cubes, and we have a 4 on the bottom. So we can write that as 1 over 4. So we have 1 over 4 times the integral of e to the u du. And now that's an integral we can actually do. We get 1 over 4 e to the u plus c. And then, okay, at the end, we should write u equals x to the 4 plus 1. So we would get a quarter e to the power of x to the 4 plus 1 plus c. Sorry, I forgot to replace u by x then. So make sure you replace u by x, a quarter e to the power of x to the 4 plus 1 plus c. Okay, so why does this work? So let's talk briefly about why it works before we do some more tricky examples. So let's suppose that we have this thing that we want to differentiate. It looks like composition function times the derivative of the inside. That's what we've been talking about. And let capital F be an antiderivative of little f. Then by the chain rule, if we differentiate capital F at g of x, then we have to do the chain rule. We get capital F prime. And since capital F is an antiderivative, capital F prime is equal to little f. So if we differentiate capital F, we get little f. We do the derivative of the outside at the inside, which is f of g of x, times the derivative of the inside, which is g prime of x. So we get the right-hand side just because we know that if capital F is the antiderivative, capital F prime is little f. Okay, so this is saying that capital F at g of x, its derivative is this thing we're trying to integrate. So capital F at g of x is an antiderivative of the thing we're trying to integrate. So that is exactly what we're looking for. So in other words, if we want to do the indefinite integral of f of g of x times g prime of x, the thing we're doing substitution with, if we want to do the, in other words, indefinite integral and antiderivative are the same thing. So we want to find an antiderivative, we should do capital F at g of x. So what is that saying? Well, first we have to find this capital F. So capital F was an antiderivative of f. So we have to find an antiderivative of f, and then we have to sub in g of x. And that's basically what the integration by substitution rule is saying, right? If we want to integrate this complicated thing, this f at g of x times g prime of x, we said, okay, we should find an antiderivative of little f, get an answer in terms of u, and then at the end write u equals g of x, so sub in g of x. So this is just based on reversing the chain rule. So a lot of the rules for integration are going to come from reversing rules for differentiation because of the fundamental theorem of calculus. So this comes from reversing the chain rule. Okay. So let's go through. So since we recognize it as reversal of the chain rule, sometimes if we see something that looks like it's going to fit into integration by substitution, we can just see that it came from applying the chain rule to something, and we can kind of guess and check the answer. So for instance, if we see integral of 2x cosine of x squared dx, well, I see it's a prime candidate for our substitution, right? U equals x squared because the derivative of the inside is multiplying. So this comes from the chain rule. So what would it come from? I have to do an antiderivative of the outside, evaluate the inside. It's going to be sine of x squared plus c. And then, okay, since I'm making an informed guess here, I should check my answer, right? So an antiderivative or an indefinite integral is an antiderivative. So we're checking that sine of x squared is really an antiderivative of the thing we started with. Okay, if we differentiate with the chain rule, we will get cosine of x squared times 2x, which is the thing we started with. Similarly, for instance, with x cubed times secant squared of x to the 4, right? We have a composition function. We have the outside, which is secant squared, times the inside. And then we have up to a constant multiple the derivative of the inside. So we guess this came from the chain rule. So we should do an antiderivative of the outside, evaluate at the inside, which will give us tangent of x to the 4, because the antiderivative of secant squared is tangent. But then we have to make sure the constants work out. So if we were to just differentiate tangent of x to the 4, we would get 4x cubed times secant squared of x to the 4. Sorry, we would get 4x cubed. Let's see, yeah. So we would get secant squared of x to the 4 times 4x cubed, which is what we had over here, but with an extra 4. So if we're going to get back exactly what we had over here, we have to make sure we divide by 4. Okay, so if we differentiate this entire right-hand side, we're going to get the derivative of the outside. So we get a quarter times secant squared of x to the 4 times the derivative of the inside, which is 4x cubed. The 4's cancel, we end up back where we started. So if we see something that looks like, a composition function times the derivative of the inside, chances are it came from the chain rule. If it's an easy one, you can just try to do it in your head and check the answer. But if you don't like to do that, that's okay. You can just apply the substitution rule. Next up, linear substitutions are always straightforward. So you can always make a linear substitution. So a substitution looks like ax plus b or at plus b or something like that, where a and b are constants. Because the derivative of a linear map is just a constant. So, and we said constants don't matter. We can always bring out the constants or move around the constants as we like. So for instance, if we were trying to find the integral of 1 over 2t plus 1 dt, well, we can make the substitution u equals 2t plus 1 for free. Okay, so because the bottom is linear. So it's a composition. The outside is 1 over u. The inside is 2t plus 1. Let's do a substitution, u equals 2t plus 1. The derivative is going to be 2. So du dt is 2. Okay, so dt is a half du if we move around our fraction. So now we can take the thing we're integrating and try to write everything in terms of our new variable u and du. So we changed the easy stuff. So we had 1 over 2t plus 1. U is equal to 2t plus 1. So we are going to get 1 over u there. And then we said dt is a half du. So we are going to change that to a half du. And then because it was a linear substitution, everything is nice and easy. There's no complicated pieces. So this becomes a half the integral of 1 over u. So we get a half ln absolute value u. Remember, the antiderivative of 1 over x is ln absolute value x. So here we get ln absolute value u plus c. And then at the end, we're supposed to replace u by whatever it was in terms of the original variable. So here it's the absolute value of 2t plus 1. So we get a half ln absolute value 2t plus 1 plus c. Okay, so let's do one more slightly harder example. Is sometimes when we use substitution, it doesn't always fit into the scheme of composition function times the derivative of the inside. So this is the nicest possible case. But there are also cases where we don't have this, where we might have a composition function, and we can try to substitute the inside. And it still works. The important thing is that when we do the same steps as we've been doing, we have to be able to always write everything in terms of the new variable and the derivative and d of the new variable. Right? We have to be able to write everything in terms of u and du. As long as we can use u equals g of x and our formula for du dx and rearrange, as long as we can use that to write everything in terms of u and du, then we're in good shape. So for example, let's look at this one, the integral of x to the 5 square root of 1 plus x squared dx. So we have that composition piece, square root of 1 plus x squared. The inside is 1 plus x squared. But we don't straight away see the derivative of 1 plus x squared, right? Because, the derivative is 2x. We don't see that, we see x to the 5. But let's see how it plays out. Let's try to use a substitution anyway, and hopefully we can write everything in terms of u and du. So we try u equals 1 plus x squared. Then du dx is going to be 2x. So we can rearrange, we get dx equals du divided by 2x. So let's go ahead and make the easy substitutions and see where we get to. So we can straight away write square root of 1 plus x squared as square root of u. We can replace dx by du divided by 2x, and then we try to cancel some stuff. Okay, so after we made that easy substitution, square root of u, du divided by 2x, we see that we can cancel an x. So we're going to have x to the 5 divided by x gives us x to the 4. And then we have a 2 on the bottom, so we're going to have a half. So we end up with the integral of a half x to the 4 square root of u du. And then remember, the important rule we said is that when we do the integration, everything has to be in terms of u and du. So we have to be able to write this x to the 4 back in terms of u if we're going to have to make any progress. So quite often in these questions, we might have a chance of doing that. Sometimes it works, sometimes it doesn't work. But here we can do that. If we want to write x to the 4 in terms of u, let's go back to our original equation that connects the x and the u. So we know that u is equal to 1 plus x squared. And if we rearrange this, we can solve x squared equals u minus 1. Okay, so x squared is going to be u minus 1. And if we square both sides, we get x to the 4 equals u minus 1 squared, just from rearranging our original equation with u and x. So x to the 4 is u minus 1 squared. And now we managed to write everything just in terms of u and du. Okay, so now we are in much better shape. We just have to do this much simpler integral, the integral of a half times u minus 1 squared square root of u. So we multiply everything out, right? We start with this term, we get u squared minus 2u plus 1. We multiply it by the square root. We collect the powers, so u squared times u to the half is u to the 5 over 2. U times u to the half is u to the 3 over 2, so we have minus 2 lots of that, plus u to the half. Okay, so we end up with this integral, and now we can apply the power rule. So if we continue, we apply the power rule, we get a half, and then you can check the numbers. But 2 over 7, u to the 7 over 2, minus 4 over 5, u to the 5 over 2, plus 2 over 3, u to the 3 over 2, and so on, plus c. And then the final step is to replace u by whatever it was in terms of x. So u was 1 plus x squared, we replace the u's by 1 plus x squared. Okay, and then we can multiply out the numbers. That's just a little bit of algebra or arithmetic, and we get our answer. So this one was slightly more complicated in that after the first step, we weren't immediately in terms of u and du. But the important step is we could go back to the original equation, and that extra x to the 4 we had lying around, we used our original equation to write, x squared is u minus 1, so x to the 4 is u minus 1 squared. So if you have some extra pieces, make sure you write it in terms of the new variable, and go back to the equation connecting the new and the old variables to try to do that. Okay, so that's everything for this time. So we said substitution is great if we're trying to integrate something that looks like composition function times the root of the inside. It also works if you only have the inside up to constant multiples. Some variance is that it always works for linear things. And it also works for a lot of cases where it doesn't quite seem to fit in the general scheme, especially with your composition functions. But the important part then is that we go back to the original variable and we manage to write everything in terms of u and du before integrating. So we cannot integrate things that are mixed that involve the new and the old variable at the same time. It has to be one or the other. Okay, thanks everyone. See you next time.